Hello everyone. So today we are going to look at a very elaborate form of deep RL architecture which was launched by DeepMind quite a few years ago. The system is called AlphaGo, and the elaborateness of its architecture actually makes it an interesting piece to study. You will see that the ideas that AlphaGo merged together actually lay the foundation of how today's large language models also work to some extent. So the system is designed to play the game of Go. So I don't assume everyone knows what Go is. So let me quickly introduce how it works. So in Go you have this 19 by 19 grid, and on every intersection you can play either a white or a black piece. You start by, I think, the white or black player moving first, doesn't matter, and the goal is to capture as many intersections as you can. Now, now the delta, the catch is what happens is if I manage to, let's say, circle my opponent's pieces at some point during the game, then these pieces get thrown out and I capture this territory. So that is basically the game. You have to circle your opponent as many times as possible without your pieces getting thrown out, and then it really becomes a very difficult game to play, as you can imagine. So this is in fact more difficult than chess, especially for a computer, because there are more moves that you can play for every position. So which is why AlphaGo was quite an achievement and a demonstration that reinforcement learning can truly scale to achieve what humans can achieve in fairly abstract settings. AlphaGo actually defeated the then world champion Lee Sedol, uh, and there's a great documentary about that match by DeepMind. You should watch, because it's basically a movie. It doesn't teach you anything about reinforcement learning as such, but I will right now. So we'll start by discussing the components of the AlphaGo architecture. So AlphaGo actually uses 3 to 4 components to check and balance each other to play the most efficient move during the game. So the first component is supervised learned policy networks. So you have two policies. One of them is called the rollout policy, and the other one is the supervised learned policy network. Now the rollout policy is a fast policy that is used for a particular form of search online, which we will look at, and the SL policy is the more important one. Then you have the refinement of this SL policy by some reinforcement learning, which gives you the reinforcement learned policy network. You have value network, which in turn is trained by regression using the reinforcement learned policy network. And with this you have the policy network and the value network, which are two out of our three components. The third component is actually used online, that is in game. It's called Monte Carlo tree search. It basically looks, the execution basically looks like this, but we'll discuss it in detail as to what this is used for. Okay, so let us start by looking at the first of the three components, the policy networks. So the policy networks are trained by supervised learning, and this is basically your pre-training. So what they do is you take a bunch of human games. What would a game look like? It would look like a sequence of state, action, and then new state, and then action again. So the training procedure for the supervised learned policy network P sigma is actually quite simple. What you do is you take a network, input a state S. From your data, you calculate what is the probability that a human expert would play a certain move, and you try to match that probability with your P sigma. So it's basically the same as classification. You have an image, what is the probability that it's a parrot? You have the usual cross entropy loss, and then using the cross entropy loss, the P sigma network learns to mimic human moves. Now there is another special policy PPI which is called a rollout policy. So since this P sigma policy is a neural network, it takes some time to execute. So it takes about 3 microseconds to actually calculate for a reasonable GPU, from a reasonable GPU, what the next action is going to be. So for one of the components of the architecture, you need a faster policy, which is the Monte Carlo tree search. So they also train what they call a rollout policy. The rollout policy is basically trained by simple linear feature regression. So we'll not go into what this means, but if you are playing chess, let's say, and I capture your knight with my knight and offer you a trade, and you can take my knight with your pawn, then the rollout policy simply says, okay, I lost my knight to the opponent's knight and I can take it, so I'll take it. So simple. Now since it is so simple, it is actually quite far from what humans would do. So it basically mimics the human move about 0.26 times, or 26% right, as against this policy which does it about 0.57. 0.57 is, by the way, very large, because you have a lot of moves you can play at the start of the game. It's basically 19 square, and then it falls with every taken position, but 0.57 is quite large. And then if you think about it, 0.26 is not very bad. This is because in general, when you have movements like capture, etc., even humans tend to just finish it off. Okay, so I hope you understood how the policy networks are trained. It is vanilla supervised learning and vanilla feature regression. Let us look at the next part. What you then do is what you would popularly know by the name of fine tuning. Once you have the pre-trained supervised learned policy P sigma, what you want to do is you want to find a computational way of fine tuning this policy. So what they basically do to fine tune this policy is make this policy play some games against itself and its previous iterations. So what you use is a mixture of opponents. So start by initializing 2 players with the same policy P sigma. Play one game, finish it off. Now once the game finishes off, you know what the reward was of every action along the game, right? Now you use that reward to reward those actions which resulted in a better outcome, and penalize those which which resulted in a worst outcome. We have seen how this is done in the previous lecture. So it basically uses reward weighted probability or reward weighted cross entropy losses, and something happened. Okay, then you update this sigma. Let's call this sigma update, and here you randomly select one among sigma and sigma update. You do the same thing again, update this sigma, p sigma plus, and here you sample among p sigma plus, p sigma plus plus. So this sampling is done because if you keep updating both, then there is a chance that you will run into a meaningless deadlock where you basically have the same policies overfitting each other without any meaningful exploration. So that is why the opponent on this side is used as a mixture. Now instead of starting off with sigma, you can also take some policies that were in the middle of your supervised training somewhere, and form a mixture a priori itself. For simplicity, I started both off with sigma, but you can take a more elaborate mixture by involving some suboptimal policies from supervised pre-training. That was your part 2. This refines your policy and gives you a policy they call P-row. Now this is a very good policy because it is trained from a warm start by human expert positions, and it is a refinement on that itself. So this is a very strong policy in itself, but they don't stop here. So if you in principle used P-row to play, you are likely to do well, but the problem is that you will often see a state where P-row doesn't have very good information, because since there are more states than there are atoms in the universe, there will always be states in the game which you haven't seen, and P-row can fail to extrapolate from there, and you may lose the game because humans will realize that what is happening. So then what you need to do is you need to build more components. So we come to our second component now, which is the value network. So what the value network does is that, given a particular policy, it gives you what is your expected reward in the game, given that you are in state S and you play with a particular policy, which in this case is P-row. Now, how do you find this value function? You just train a neural network V theta, which is a value network, using the simulated data set. So let me mention in particular how they do it. So you start at a state S, make both opponents play P-row. The game eventually reaches the end, so you know what the reward is. So if the opponent wins, you give him the positive reward, and if he loses, you give him 0, something like that. And so since this is probabilistic, you will have to run multiple iterations, and this lets you produce a state to reward map. Now this is your data set, and you use this data set to train this network. So you input S here, and V theta of S should be close to your simulated V of S. So this is vanilla regression, and in regression you use this square loss function, which gives you this gradient update that I have put in as an equation. Okay, fantastic. So then these two components are ready. Your policy network is ready and your value network is ready. Now we come to a very elaborate component of the AlphaGo architecture, which is actually also the which was also a popular methodology to train reinforcement learned systems before deep learning was involved. So if you know that if you know Stockfish, which is a chess engine, it was trained in the pre deep learning era using Monte Carlo tree search. So let's see how what Monte Carlo tree search is, and how it's used. So it is important to understand that Monte Carlo tree search is an online procedure, which means that this runs in game. So once your opponent makes a move and puts you in a particular state, Monte Carlo tree search begins then. So suppose that you played something with some policy to start with, because why not, and then your opponent responds in some way, then you end up in a particular state S here. Now if I were just using these two uh, the previously two trained policy and value networks to make a new move, what will I do? I will either just sample out of Piro a particular action and just play it. Okay, good enough. Otherwise, I can do something more elaborate where I see, okay, what is the value function I get from playing that action, and then make a weighted decision as to value the value function and policy, let's say, equally, and make a weighted decision. Now Monte Carlo tree search is a more elaborate way of doing exactly that, except that you use the in-game computation available to create to search more and make an informed decision, because you would like to look at more states that come out of the state your opponent has put you in, because it is likely that you have never seen that state, since there are so many. So when you start in this state, this is basically a leaf node L. Now what happens is, at a leaf node is basically a node which you haven't seen before. Now you start on the leaf node, and what you do is you have this fast policy ppi, and you roll out the game with policy ppi multiple times to get an idea as to what the cost to go is from this state. That's your rollout, and given that rollout, you have a basic idea of what the reward is ahead of this state. So that is your ZL. Okay, now you also have our policy network, value network, that we had trained by regression. So this is, then you ascribe this value to the leaf node, or to the node that we began at. Now once you do that, this is no longer a leaf node, because you have seen it now, you have done everything. So now you play the next action and then begin again. So you play some action A and you go to the next node, which is now the new leaf node, and this basically iterates. Now when you begin from this leaf node, you can initialize the likelihood of every action you take some way. So it is usually initialized by p of s comma a, which is initial probability, and actually they use the human expert probability for this, and not the P-row, which was the refined one. Because uh, if you use the human expert one, since humans are believed to be more creative, this actually gives you a more diverse choice. Now once you are done with this, you basically keep repeating this until you reach a reasonable depth, or you reach the basically terminal state of the game, which is basically game ends enough times. And once you have run enough simulations, you take a weighted decision. So we can basically see what happens online in this particular example, where the network was playing against the European champion. So let us look at this. So the network is supposed to put a black piece somewhere. Now it's turn to play, and what the value network v theta is telling the network in this state is that this orange circle is basically the best move. Okay, now now what it does is it takes the policy p pi and rolls out all the possibilities for every move down the tree. So this is your rollout policy. Remember, this is very fast. And what the rollout evaluation then tells you, which is basically the ZL of this state S, is that it is this move which won the most when the rollout policy was being used. Okay, now what you do is you basically do a weighted sum where you give some lambda importance to v theta plus 1 minus lambda importance to the rollout probability, and then this is what your value network looks like. Okay, and then it further trains down the line to sort of refine again and again. So it basically starts from this value network. Now this is no longer your leaf node, so you have the probabilities for every action from this state fixed now, and then you start from new nodes as your leaf nodes and do the whole process again, and this simulation runs multiple times. By the way, this is what the policy network was telling him, that it should play with 0.6 probability it should play this move, and with 0.35 probability it should play this move. Okay, now once the repeated simulations along the Monte Carlo tree search are run, the decision is then taken by how many times you have visited a particular leaf. So once you run this simulation, note that the action taken during simulation is basically what maximizes the expected reward. So which is why it is a good strategy to, at the end of several simulations, to just choose what was visited most times, or what is more likely to give you a better reward. And then, as you can see, 79% of the time this was played during the simulation. So then it chooses this particular move, and then it played this move. Now the opponent actually played this white square as a response, but the network was suggesting that the opponent should have in fact played this move, and in the post game evaluation the opponent said, okay, that move is indeed better. So I hope you have a grasp of how AlphaGo works from this discussion. It basically has these three components, two of which are trained by supervised learning, and some fine tuning using reinforcement learning, And the Monte Carlo tree search is actually Monte Carlo research is actually the common way of doing reinforcement learning without using neural networks. And what 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 AlphaGo did was combine neural network based learning, which captures more variety of features, and and Monte Carlo research, and it basically resulted in a very powerful system that was state of the art back then and defeated the world champion. So it was basically a proof of concept that reinforcement learning can in fact learn uh, policies in a very large and complex state space. Thank you. That will be all today. Next time we will look at either language models or try to implement something in a notebook.